Hi, this is Steve and welcome to our video series. In this segment we're going to continue our introductory presentation with part 2. So let's first just review what we did in part 1. In part 1 we looked at what an iFLOW system could be, and we looked at the various mix and match options for both gas and electric. We looked at gas tankless, boiler, combi boiler. On the electric side, we looked at electric water heater, heat pump water heater, and a heat pump itself, and any combination of those if we want gas and electric. We looked at the need for variable speed and the advantages of the lower minimum inputs, resulting in better efficiency and better comfort. We reviewed the testing results of heating loads on average single-family homes in both the US and Canada, and then we combined the efficiency ratings and overlaid them over those heating loads to get a better understanding of why the lower inputs are necessary and how that turn down ratio when we look at the heating loads is instrumental in determining the advantages of a combi system over a traditional HVAC system, let's say a furnace and water heater. So again, the theme of the first part was less cycling, better efficiency, and better comfort. So in part 2, we're going to examine some CSA P911 testing results. The P911 is the combination systems testing efficiency standard developed by CSA and used extensively in Canada. We'll look at some of the factors that contribute to making the best combi systems. So what makes a good combi system? What makes a poor combi system? Are they all the same? Can I mix and match anything, any components out there and get decent results? We'll look at some of those factors. We'll look at the heating formulas, right? When we're heating air with water, right? We're transferring the btus from the water source over to the air side and delivering them through the house. So we're going to look at the formulas that we use, and that will determine which variables we should be focusing on and then how we adjust those variables to maximize the efficiency of the system. We'll look at the iFLOW options that complete the package, so the optional accessories that complete the package and make the installations quicker and easier. So let's start. Here's the question: Is any combination system better? So again, in part 1, we looked at how a combi system can outperform traditional furnaces, and the reason was because of the lower turn down, the lower minimum input, less cycling, better comfort. Now the question is any combi system going to be better than a furnace? So what do you think? And let's preface that by looking at a couple of options or a couple of points. So first, I get this feedback all the time. Well, you know, an air handler is just an air handler. It's a box with a blower and it blows air across the coil and you get the heat transfer. Okay. So are they all alike? Is it just a blower and a coil in a box? They can't be that different, can they? So the question for you: if you paired an air handler with any heat source, the combined efficiency when space heating will likely be close to the efficiency of the heat source. Could be boiler, combi boiler, tankless, tank type water heater, whatever the case may be. So for example, let's say I took a 95% AFUE boiler and paired it with the iFLOW. Would it make sense intuitively that the heating performance of the iFLOW would be 85 or 95%, similar to the AFUE of the boiler? Or if I paired it with an electric water heater that has a UEF of 0.94, would the resulting efficiency be 0.94, 0.93, somewhere in that range? What do you think? You know, intuitively, it might sound like it would make sense, but actually the results are showing different. And that was the purpose for CSA developing the P911 standard. So it is a test method for determining the performance of combi systems, or combined space and water heating systems for the gas side, for the gas appliances. So again, P911, all of the results that are listed are on the Natural Resources Canada website, so it's all public information. So any of the information I'm going to show here is all public information. Anybody can download it, anybody can sort through the data. So again, it's on the the Natural Resources Canada website. Again, that's the Government of Canada site. That would be the equivalent, let's say, of the DOE of Canada. But you can go onto the site, you can download the entire format, you can search for whatever criteria you want perhaps. This is a snapshot of some of the results. I've selected these results to show differential. I'm not trying to single out any manufacturer over the other. We've all tested. All the results are publicly available. But there are some differences that you need to be aware of, and some significant differences. So let's take a look. So for example, Rinnai tested their RU160IN, that is the Rinnai Sensei model, that's one of their newer models. And they tested with the Aspen air handler. They tested with a Taco 008 pump. And they scored here the TPF, which is the resulting combi score. They scored a 0.73. Okay, a 0.73. They tested their RU160IN with Hy-Vee systems from this is ESP out of Edmonton, so a Canadian air handler manufacturer out of Edmonton. They tested with the HEP50 coil with a Grundfos 1558, and they scored a 0.72. So why do I show you these numbers? 0.73, 0.72. The scale goes right up to 98. You can see all the numbers in between. But I just wanted to point out a significant difference. This is the same Rinnai unit, the same RU160IN, the same that was tested down here. Difference being, this is iFLOW now, this was Aspen, this was ESP. Grundfos, 1558, 1558, same pump. So, testing to the same standard, the P911 standard, testing at the same lab, testing with the same heat source, testing with the same pump. What are the results for Rinnai and iFLOW? 0.94. This shows that the Rinnai has the capability of scoring very high on the P911 test. But it also shows that it can score quite poorly as well. What's the difference? The air handler. The heat source is the same, the pump is the same, the testing methodology is the same, the lab's the same. The only difference is the performance of the air handler. This is the difference. So, back to our question, not all air handlers are made the same. There are things that we do that other manufacturers don't do. And that results in efficiency gains. And not insignificant, not 1 point, 2 points, 3 points, 5 points perhaps. No, 0.72 to 0.94. That's a 22% increase. Or 0.73 to 0.94, 21% increase. That's a huge difference. That's the difference between the highest condensing and mid efficiency. Right? You take a 90 or an 80% furnace and then compare another 20%, you're up to the high 90s. So this is a significant difference. So do not assume that that a contractor is going to be able to go to an HVAC wholesaler and buy an air handler, pair it with a boiler, or pair it with a tankless, or pair it with a heat pump water heater, and score great results. That is not what these tests are showing. Another example. So now we're looking at Navien as a heat source. So now we have the NP180A with, again, Hy-Vee out of Edmonton. and this time they scored a 0.86, and then iFLOW with that same 180A, iFLOW scored a 0.98. So 12% difference. Again, that's the difference between non-condensing and condensing. Right? We're going 86, so if you 86 to 98, somewhere in that range. So it's significant. And just another look. So again, this is Rheem in blue. So there are 3 test results from Rheem where they tested their condensing, right? Condensing residential tankless gas unit, 95% direct vent. And they tested with their own air handler using a Taco 009 pump inside. And they scored a 0.8 to 0.8 and a 0.82. So 80 to 82. All to say this is Rheem with their own tankless water heater and their own and their own air handler, trying to score better marks, but only able to score an 80. So again, it's not that easy. It's not that simple. And again, don't expect and don't think that you can just pull as a contractor or as a wholesaler, just mix and match stuff that isn't tested and assume that you're going to get great results. That is not the case. And that was the purpose of this P911 test, so that we can quantify the performance of these combi systems and demonstrate your capabilities. So the question is, can I use any heat source? Well, no. There are certain heat sources that will perform much better than others. We have the best performers in Tier 1, we have the mediocre performers in 2, and then we have the good, or depending on what your expectations for good, in Tier 3. So what makes a better heat source? As we saw by the previous slide, you can have significant differences in operation. The heat sources can perform well, they can perform poorly. The air handlers can perform well, they can perform poorly, giving you different results. So in general, on the electric side, if we're going to put a heat pump water heater in there, we want a heat pump that performs at a 3 level. There are some that perform at 2, 2.4. Why don't we go with 3 if we're going to choose a best? Right? Okay, that's going to be the best in that category. On the gas side, we're going to want to go with a unit that has a very high turn-down ratio. As we saw in part 1, the lower we can get the input of the gas appliance, the better it's going to match our heating loads. And our loads are much lower these days than they used to be. So the lower we can get the input, the better it's going to be. So I would say a minimum of 10 to 1 turn down ratio would be the expectation for a Tier 1 performance unit. So if it's 100,000 BTUs, at least a 10 to 1 going down to 10,000 BTUs. If it's 200,000 BTUs, again, at least a 10 to 1 going down to 20,000. But there are some manufacturers, Navien in particular, I'll mention, is now 15 to 1 turn down on their units, on both some of the combi boilers and the tankless, which means you have a 200,000 BTU input, gives you lots of domestic water capability, but can also modulate down to 13,000 BTUs on the minimum input. And then the 150,000 BTU model, right, the NPE 180 A2 or S2, for example, at 150,000 BTU input can go right down to 10,000. So the closer we can match that lower input to the actual heating load, the better it's going to be. Why? Less cycling, better performance, better comfort. So those are the 2 key inputs. So with a tankless, again, we want at least a 10 to 1 or better turn down ratio. Same with the combi boilers, 10 to 1. Any boiler that has an input greater than, again, we want that same. We want a minimum input of, or minimum AFU of 0.95. We want a minimum of 10 to 1 turn down ratio on that. We're going to add another criteria. We want to be able to have at least 2 temperatures. We want to have the domestic temperature for any of the domestic devices or combi boilers. We want a set temperature for the domestic, but then we also want a set temperature for the heating. And why is that important? Well, your domestic water temperature is going to be set likely 120, 125, maybe 130, but usually on the domestic side it's between 120 and 125 on the tankless and on the combi boiler. But on the heating side, we may need to go higher than that. And why? Well, this is just a capacity chart. This is similar for most manufacturers, where it will outline at different temperatures, at different entering water temperatures. So we start at 120, 130, go right up to 180. On the different models, I can actually deliver more BTUs. Right? So going from, if I'm supplying my air handler at 120 with 120 degree water, I can supply almost 28,000 BTUs. But if I increase that to 180 degrees, now I can supply almost 63,000 BTUs. So a significant difference, more than twice the amount of heat just by increasing the supply water temperature. So this is common for all air handlers. As we increase the supply temperature, the amount of BTUs we can deliver increases. So why is this important? So as we go into the winter and we need to deliver more BTUs into the home, if we can supply a gradually increasing temperature, then we can meet the heat load. So as the heat load in the home increases, we can meet that demand, but we can run at significant or at increasingly warmer temperatures to meet those BTUs. Now, why is that important? Well, we could set the unit to operate at 180 degrees all year round, but what that means is you're always delivering that 180 degrees when you actually don't need it. If I don't need 62,000 BTUs in October, why do I need to deliver that? Maybe I could run at 140 degrees. That 140 degrees, and why is that important? Because the lower the operating temperature, the lower the supply temperature, the lower the return water temperature, typically, the more condensing you're going to get out of your gas appliance. So this is kind of how it all works together. So if we can operate at lower temperatures, delivering lower BTUs, it's going to be fine. Now, we can also play some games with the unit itself. So for example, if I'm using my smallest unit, at 180 it's capable of delivering 80,000 or 63,000 BTUs. So let's say I need 60,000 on my design side. Okay. Well, if I step up in size, if I go to a larger coil, more surface area, more transfer area, then at a lower temperature, I can actually get the same amount of BTUs. Now, if I step up to one more size, now I'm going up to my largest size, it can actually do 95,000 BTUs, but it can also do 60,000 BTUs at 140 degrees. So I can look at my design criteria. So for example, most of the tankless water heaters top out at 140 degrees on the residential versions. They can go into the commercial versions and get higher temperatures, but on the residential, oftentimes there's a lock at 140. So if I'm sizing my system and I need 60,000 BTUs for my design, I'm going to say, okay, well, if I can set my tankless at 140, can I use this model, the 14,000? No, because I'm only able to supply 40,000 at that temperature, even though on the spec it can deliver 63, but it can deliver 63 at 180 degrees. So then I go to my 16,000. Okay, I'm only 48,000, so still a little short from my design at 60. So I'm going to step up one more. Oh, my 18,000 BTU, my 18,000 series can go up to 60,000 at 140 degrees, so that's the one I would choose if my heat source was, let's say, top limit temperature-wise at 140. So all to say, if we can have a system that can operate at two temperatures, let's say a domestic temperature, 120, 125, but that can also work at a heating temperature, whether that's 140, whether that's 160, whatever your design is, and again, you can mix and match the different models to make those selections. But if we go back, all to say that something that can provide at least two temperatures would be better than one temperature. Even better than that is something that has what we call outdoor reset. Outdoor reset is coming from the hydronic side. Most of the boilers these days, most of the condensing boilers will have outdoor reset. And what it is, it's the ability, we have an outdoor sensor that's looking at the outdoor temperature continuously. And as that temperature starts to decrease outside, it will automatically increase the supply water temperature. Why? To deliver more BTUs. So for example, maybe in September when I need only 3,000-4,000 BTUs, maybe 120 is more than enough on my smallest unit to deliver that. So that, fair enough. But I get into October, into November, into December, now into January, I might need 180. So if I can have this sensor, and if it can speak to the unit and automatically adjust the heat source to supply warmer and warmer temperatures, that's going to be ideal. So many of the boilers have outdoor reset, right? So they have that ability to adjust. So if we pair the iFLOW with a boiler or a combi boiler, a boiler or a combi boiler that has a good turn down ratio, let's say a 10-to-1 turn down ratio, and it has outdoor reset, we're going to get some very, very good results with that boiler, no question about it. If we have a tankless that only has one set point, right? It doesn't have two set points, right? It only has one set point. Maybe set it at 140 or 160 or 180, depending. If I only have one set point and I need, I've designed it because I've selected this model, so I actually need 180 degrees because I need the 60,000 BTUs. Okay, well I have to set my unit, my tankless unit, then at 180 degrees. It's going to operate at that temperature all year round. So on the domestic side, you definitely need a mixing valve, right? That is mandatory because these are scalding temperatures. So you need a mixing valve on the domestic to temper it down to 120, so an anti-scald. But what it means is I'm going to be operating. So even in September, when maybe I could have gotten by with 120, but because I don't have that automatic adjustment, I'm running at 180. So I'm delivering too many BTUs, and as a result, I'm going to start cycling. And then in addition, I'm running at those hotter temperatures. So when I'm running at those hotter temperatures, I'm pulling more scale out of the water. So for a number of reasons, it's not great to operate at. Additionally, on the efficiency side, if I'm running at 180 degrees and I'm supplying 180 into the coil, at what temperature do I need to go back to the heat source if it's a gas appliance to start condensing? Condensing usually starts about 100 or stops about 137. So I need, depending on the dew point and where you are, but I need to be, let's say, below 140, below 135 to get any condensing at all. So if I'm at 180, that means I need a minimum of a 45 degree delta T across the coil. Well, what's the average delta T across coil? 20 to 30. So if I'm at 180, even taking 30 degrees off, I'm still at 150. I'm not condensing back to my heat source. So that's the disadvantage. So all to say, we're looking at here what makes a better heat source and what makes not so good heat source. Well, that's the main determinant. High turn down ratio, at least 10-to-1, 15-to-1 if we can get it. On the smaller boilers, now here's the issue. On the smaller boilers, let's say 60,000 BTUs and below, it's really hard to turn down that gas valve more. So on the smaller boilers, let's say 60,000 BTUs and less, we'll want an AFUE of 95, but a turn down ratio of, let's say, a minimum of 7-to-1. So on the 100,000 BTUs, we're going, or anything more than 60, we want 10-to-1, but on the 60,000 and lower, we're going to go 7-to-1, right? Because the minimum input is going to be around 7,000 BTUs. It's really hard to get it down to 6,000 or 5,000 BTUs, if you will. So that's what we would suggest as we'll create a tier 1 performing heat source. So a high UEF on the water heater side, heat pump of 3 or greater. On the tankless, a UEF of 95 or greater with a 10-to-1 turn down and with an outdoor temperature sensor capability. Combi boiler, 95 AFUE, 10-to-1 turn down, outdoor reset definitely. Boilers above 60, same 95,000, 10-to-1 turn down, outdoor reset. Boilers under 60,000 and under, then we're going to go 95% AFUE, with a turn down of 7 to 1. Okay, so that's our category 1. Category 2 would be anything below that. Well, let's just go to the lowest category. So category 3 would be electric water heater, where I've got a UEF of 0.93. Sounds good, and may perform quite well. Why is it category 3? Well, because we've got category 1 having heat pump water heaters with a UEF of 3 times the efficiency of this. Now, in the middle of winter, because the heat pump won't be able to get all of that, it's probably going to be operating on electric backup for the colder months, right? Maybe December, January, February, March, perhaps. But nonetheless, even in those colder months, it's going to be probably at least this UEF of 0.93. But in the shoulder seasons, the heat pump should be able to pull some heat out. So the average efficiency will be higher than this. So if we're looking at electric, that's why we have the good and bad. If we're looking at gas, well, if we have a tankless water heater with a UEF of 0.93 or greater, for example, a turn down ratio of maybe 8 to 1, again, not as good as our 10 to 1 or 15 to 1, and then we don't have any two temperature system. This is going to make it such that this is a tier 3 solution, unfortunately. Even though on the domestic side it can perform quite well with a UEF of 0.93, when we get it in combination in heating, it's not going to perform anywhere near what the tier 1 sources will be. So I'm going to leave it there. We can go on and look. The tier 2 obviously is somewhere in between those two. And now let's look at the air handler. So can I use any air handler? So if I choose a tier 1 heat source, right, water-based heat source, can then I choose any air handler? Right? If I choose a great heat source, pair it up. Well, we saw by the results of the P9 testing that that's not the case, where we can take the same high-performing heat source, pair it with a different air handler to the same test, to the same, using the same pump, and they perform very differently. So let's look at what we can do on the air handler side. Well, let's go to the bottom first, because this is quite simple. Again, we've got a good, better, best type of scenario, even though good may not be good depending on your expectation of heating. If you think heating in the 70s and 60s is good, then that could be a solution for you. What a tier 3 or a bottom, a very, let's say in our good category, a PSC motor, so no modulation, no ECM motor, you just have a single speed PSC motor. You've got a 2-row coil minimum, let's say 2 or 3-row coil. You've got a single speed circulator. You don't have any temperature control. You don't have any delta T control across the coil. Basically, you're getting a signal to come on, and you're running the blower at a single speed, and it's basically blowing air. That's all it does. If you have that as your as your air handler, you're likely going to get a heat performance, even with the tier 1 heat source, you're going to get a performance of likely in the low 70s. And we'll show you some of those results. Okay, so how can I get a better air handler? Well, the more we add to the air handler, the better the performance is going to be. Excuse me. So, for example, instead of the PSC motor, a tier 1 unit is definitely going to have a constant CFM ECM motor. So there are a couple of types of ECMs. There is a constant torque, which was kind of your entry-level ECM. It allows you to set basically 5 different speeds, of which many manufacturers only use 3 because their control can't do 3, or it's a little bit more complicated, but they'll set 3 speeds: low, medium, high. 400 CFM, 600 CFM, 800 CFM. 600, 800, 1000, whatever. You can get all different mix and matches, but typically that constant torque, so we're going to throw that in a tier 2 because it doesn't have full variability. It's running at 3 speeds basically, maybe 5 at most, but 3 speeds typically. Whereas the constant CFM ECM is your full variable speed. It's your higher end ECM. There is a significant price difference between those two, like hundreds of dollars. So don't think that just because it's an ECM, they're exactly the same. They are not. Very different in terms of operation, very different in terms of performance, very different in terms of cost. So that would be one. A minimum, a tier 1 will have a minimum of a 4-row coil. It could be more, but at least 4 rows. You're going to have some integrated pump control, whether you're integrating an ECM or whether you're integrating some sort of variable speed pumping like we do in the iFLOW. You're going to have some sort of variable speed control there. You're going to definitely need some strategy to maximize the delta T, or some flow performance or coil monitoring strategy to allow you to adjust some of the variables to optimize the system, whatever that company's optimization strategy is. So there's not one strategy, there's not one way of doing things, but if they don't have any strategy, then you're going to be here in the 60s, in the low tier 1, or the tier 3 lowest solution. But anywhere in between there, you could fall out and get some better results. One thing that in coordination with the heat source, when we look at the heat sources, again, we're trying to look at heat sources that have a high turndown ratio. Why? Because that minimum input is very important. Now, if the minimum input is 20,000 BTUs and the heat load is, going to be below 20,000 often, it's going to short cycle, right? It's going to cycle off and you're going to post-purge some of the heat out, and then it's going to have to come on again, reheat, and then deliver. So you're going to get some losses. On the air handler side, if you have a strategy, if the company has a strategy to recover some of that heat when the heat source is cycling, that's going to be advantageous as well, right? So this is how we can, again, recover some of that heat. So even when we're cycling on the low loads, we're recovering a lot of that heat instead of wasting it out on the exhaust side. That's going to get you some additional points. Obviously, the outdoor temperature sensor, whether it's on the heat source or whether it's on the air handler, you should have it. But we have it on the iFLOW has it on the air side as well. So we're measuring and varying our delivery of heat into the home based on the outdoor temperature. So if the heat source has its own outdoor temperature sensor and it's adjusting its temperature delivery, we also on the iFLOW side have an outdoor temperature sensor which allows us to vary the target BTUs into the house on the air side. So we're matching. So that'll get you some additional points too. So anyway, all to say, variable speed ECM, a minimum of 4-row coil, a delta T strategy to maximize or optimize the system efficiency, a strategy for recovering the heat when your heat source is cycling on low BTU loads. Those will give you the better performing air handlers. And then tier 2 will be somewhere in between those. So when we put that mix and match of heat tier 1, tier 2, tier 3 heat sources and pair that with tier 1, tier 2, tier 3 air handlers, we get a matrix. And those matrix will deliver, this matrix will deliver some variability in performance. If you have a tier 1 heat source and a tier 1 air handler, you're going to get results in the 92 to 98% range. No question. Right? You've got full variability, full temperature control on the heat source, and then you've got some great strategies on the hydronic side. No problem. You're going to hit this range all the time. That said, if you have a tier 3 heat source and a tier 3 air handler, look at where you're going to be. You're going to be in the low 70s at best. So, all to say, no, you cannot just pair any air handler with any heat source and get a good result as a combi system. There are things that make a good combi system, and we reviewed some of them. But here's the variance across those. So I will leave that to you. If you have any questions on that, you can by all means reach out, and we can provide more detail on what some of those metrics would be. So now let's look at what makes iFLOW unique. So let's start by looking at the technical basis, right? We've got heating forced air with water. Right? So that's what we're doing. We're heating water, and then we're taking the btus from the water and we're transferring it to the air. So how do we do that? Well, we've got some formulas. We've got output heating BTU formula, right? Obviously, output is your input times your efficiency. That gives us our output. So we're dealing with only output. To get the output, we have their GPM rate times our delta T water times 500. So for example, if I want 60,000 BTUs, I could have 1.5 gallons a minute times an 8-degree delta T times 500, and that'll give me 60,000 BTUs. On the air side, again, my output, BTU, that's CFM times delta T air times this constant of 1.05. So again, there's an example. If I need 60,000 BTUs, let's say I have a 50-degree delta T times 1.5, and then I'm looking at about 1100 CFM to get 60,000. So again, why 60,000? Well, let's just continue from our part A, where we are looking at a 60,000 BTU load in a 60,000 BTU house. If I need 60,000 BTUs on the heat side, right, in my house, then I need to pull 60,000 BTUs worth of heat from the water side. So I need to know how many GPM. I need to know my delta T water. Why? Because I need to know how many BTUs I'm pulling. Why? Because I need to deliver that 60,000 BTUs on the heating side, on the air side. I need to transfer it to the air side. So, if I need 60,000 BTUs on the air side, and then I need 60,000 BTUs on my source side, on the water side, to meet that, then these two equations I can equate to each other. Right? So this equation, the water heating formula, needs to match the air side or I won't be balanced. Right? How can I deliver 60,000 BTUs worth of warm air into a house if I only have 30,000 BTUs from my heat source? Impossible. They have to match. We at iFLOW have to make that match. We have to be able to pull the 60,000 BTUs from the water side and deliver it to the air side. So we're watching those numbers. So all to say, we're going to equate these two formulas. So we get this. We get GPM times delta T water times 500. So this is our water side. And that has to equal the air side, right? The CFM times the delta T air times 1.085. So when we equate these two and then simplify, we just simplify on the constant side, and we basically get CFM, right? CFM times delta T air divided by GPM times delta T water gives us this. So all to say, we're not going to really look at the formula, but we're going to look at those variables, because those are the variables that we need to focus on. What are those variables? CFM, and then the delta T air. What's my return? What's my supply? That's going to determine, in conjunction with the CFM that I'm delivering, how many BTUs I'm delivering into the house. And then on the water side, I need to look at my GPM and my delta T across the hydronic coil, my delta T water. That's going to determine how many BTUs I'm getting from my source side, so that I can deliver then on the air side. So those are the four variables that we need to really focus on: GPM, delta T water, CFM, and delta T air. Right? Those need to be controlled properly to deliver the heat from the water over to the air. So we're looking at how we at iFLOW now do this. So iFLOW controls each of those variables. So let's look at the water side. iFLOW controls the GPM rate. So the GPM is the gallons per minute. That's the amount of flow we're putting through the heat source and pulling back. So iFLOW incorporates variable speed pump control on our PCB. So you don't need to buy an expensive ECM pump. You can buy a single speed pump. We supply a pump with our kits, our plumbing kit, our easy plumbing kit, and our boiler kit. We supply a Grundfos 1558, which we can vary. So we vary the speed and the of that pump on our controller. So there is nothing you need to do. You wire your pump into our C1 and N contact, and then we supply variable speed. So again, no need for an expensive pump. So we're controlling that factor, and we can control that pump from 35% right up to 100%. Right? So we've got the ability in terms of the flow. We can flow from about 0.6, 0.7 right up to 3.6 approximately through a tankless water heater. So all of our numbers are designed around a 3 GPM. So we're using a small, relatively economical pump, but we're making it a high performance ECM and varying the pump speeds as we need. Why do we need to vary the pump speed? Because we're trying to control the delta T water. So if we increase or decrease the speed of the pump, we're going to see an offsetting increase or decrease in the delta T across the hydronic coil. So how do we do that? Well, on the iFLOW we have a temperature sensor on the hot supply. We also have another temperature sensor on the cold return. So we actually see the delta T across the hydronic coil. So we're looking at it, measuring it, monitoring it continuously, and then dynamically adjusting the GPM rate to maintain a very, very high delta T. Again, as I said, most air handlers are looking at an average delta T of about 20 to 30 degrees Fahrenheit. We are getting most of the time between 45 and 60 degree delta T's across our hydronic coil. That's giving us more BTU performance, but a lower return water temperature for the heat source, so we're getting better condensing and thus better results. So this is what we're doing. So we're measuring the delta T continuously by our two sensors and adjusting the GPM rate to maintain that high delta T. Okay, so that's on the water side. What about on the air side? So on the air side, now we have CFM and we have delta T air. Okay, so how do we control the CFM? Well, the iFLOW employs a 100% variable speed blower. We're using a Gentech Eon blower. So for those that are familiar with Gentech, you can use the same diagnostic tools that you would use on any Gentech motor. You can use it on this one as well, of course. But then with our advanced software, we're controlling that ECM in 1% increments. So I can go from 5% to 6% to 7%. I can go from 32 to 33, 34. I can go to 89, 80, 89, 90, 91. I can dial in the CFM I need exactly and precisely to what I need to deliver on the air side. Now, why do I need to do that? Because the CFM, in accordance with the GPM and the delta T across the water side, that's going to play with the BTUs that I need to deliver. So I can adjust these variables and play. Now, let's say I have a system that was designed for 800 CFM. So I ramp up my blower at 800 CFM. Oh, it's noisy. So there was either an issue with the installation or something didn't go right in the design. It happens. Okay, so maybe I need to reduce that blower motor down to 650. When I get it down to 650, now it's nice and quiet. At 800, the design, it was too noisy. Okay, so I bring it down to 850, great. Or sorry, 650, now it's quiet. Okay, well now it's 650, but now I need to make up the BTUs because I'm running at a lower CFM. Well, okay, what if I increase the GPM? What if I increase the delta T? Can I get more BTUs per CFM? Right? So we can play with the variables to achieve the objectives we need, right? Which is something that no other manufacturer can do. Okay, before I move on. So that CFM that we use is a constant CFM ECM blower, as I mentioned earlier when we were talking about the specs. So this blower will maintain the CFM delivery even as the static increases. So over time, as our filter gets clogged, the blower will ramp up to maintain the CFM. Or if I've designed it around a 0.6 inch static, but maybe it turns out it's 0.8 or 0.9 or 1 inch static, then the blower will just use a little bit more energy, right? It's going to use a little bit more power, but it will maintain the CFM. So again, it's got that full variable speed to maintain the CFM. So when we calculate our target BTUs, the house needs, it's a late October night, it needs 18,000 BTUs, okay? 18,000 BTUs, so the iFLOW will look at GPM, delta T water, CFM, delta T air, and transfer 18,000 BTUs worth of heating into the home. So we know what we need to target in terms of CFM. Now, if the static is increasing, then we need to maintain that CFM, because we need to deliver that same BTU into the house. We can increase the power to the motor, and that's done automatically to maintain the CFM. So that's the constant CFM, and that's the difference between torque. The torque, constant torque, will maintain the torque, but you're not going to maintain the CFM. Anyway, so now delta T air. So now on the iFLOW, we are measuring, so on the top of our hydronic coil, we have this sensor. This is measuring the discharge temperature coming off the top of the coil, so we know what our supply air temperature is. And then we have a return air temperature sensor on the blower, right? It's on the inlet of the blower. So as the air comes into the blower motor, we're sensing the air temperature there. So we know what our delta T air is. So as we know what our delta T air is, we can then adjust the CFM, and again, the GPM, the delta T hydronic, or the delta T water, to, again, deliver the CFM, or deliver the BTUs that we need into the space, ultra steady temperatures, best comfort that you can find by playing with each of those variables. So that's how we do it on the iFLOW side. Now, knowing what those input variables are, and knowing what those variables are and the different delta T's are great, but now we need some sort of controller to be able to process all those inputs, decide what we need to do, and then output, right? Then make it happen. Our board is likely the most complex, not the most, I'm not going to say complex because it's quite simple, which we do all the complex stuff on board, but it's the most advanced controller that you'll likely see in the HVAC industry, because we are taking all of those inputs and we are managing those and then outputting to maximize the efficiency of the system and the comfort of the system. This is our 4-zone controller. All of our thermostats wire, so these are 4 zones of thermostats, and we have our dampers, so we have zone dampers that will connect to the system. We have a supply damper, a return damper, and then temperature sensors in each of our dampers. So there are lots of inputs going into the iFLOW, and then we're calculating what we need to do, and then we're outputting. So again, it will be the most advanced HVAC controller that you'll likely see on the market. Okay, so I mentioned outdoor reset. I mentioned outdoor reset when we were talking about some of the features that will make you a Tier 1 performing air handler. Outdoor reset is, in our opinion, critical. So, in each iFLOW, each Wi-Fi model and zoning model doesn't come with the base model, but you can attach it as an option if you want it. You will get this outdoor reset sensor. That outdoor reset sensor measures the outdoor temperature. So where should it be? It should be somewhere out on the exterior of the building, not in the sun, if preferably, not exposed to any other exhausts so it can heat up, so that it's sensing the actual proper temperature. What does that do? Well, that sensor is going to read the outdoor temperature, right? And if it's 70 degrees or above, it's going to say you don't need any heating. So even if the thermostat calls for heating, it's basically going to turn the system off, right? Because it says, hey, it's 70 degrees outside, you shouldn't need any heating. And then the other side, the other end of that slope, is where you need maximum. So when you look at, if it's new construction, for example, you look at your design spec and you say, okay, what's my outdoor design temperature? Is it 10? Is it 20? Is it minus 10 Fahrenheit? Is it on the Celsius scale? Is it minus 15? Is it minus 20? Is it 0? Depending on where you are in the country, right? North, south, east, west, you're going to have a different design temperature. This is where you set, right, your design temperature. So it could go this way, which will change the slope of the line, or it could go further this way, which will again change the slope. So all we're doing is we're changing the slope of the line. Now what does that change in slope do? Well, for example, let's just pick a random temperature. Let's say it's 30 degrees outside, which is 30 degrees Fahrenheit or minus 1 Celsius. So if it's 30 degrees Celsius outside, then we go up to the slope, we go across to our BTUs, and we're going to target to deliver 57,500 BTUs into the home. Right? So this is our target based on that temperature. Now, if the temperature is 50 degrees outside, so let's say it's 10 degrees Celsius, 50 Fahrenheit, now I'm going to go up to the line, I'm going to deliver, and I'm only delivering 27,500. So this is the value of the outdoor sensor. It's going to create a slope. Right? We've got our design temperature, and we've got our outdoor temperature at 70 where it goes automatically off. This is preset, can't be adjusted. This is fully adjustable depending on where you are in the country. But that slope is going to determine how many BTUs we are targeting to deliver into your home. And it's based on what's happening outside. As it gets colder outside, we know you're going to need more BTUs on the inside, and vice versa. As we go from winter into spring, we're going to need gradually less. So, again, this is the advantage of the ability to adjust the outdoor temperature, but also we can adjust the BTUs as well. So let's say we install the iFLOW 18,000 series. It has a capability of doing 95,000 BTUs, but let's say our heat load is only 60,000 BTUs or 50,000 BTUs. We can then go in to our controller and we can adjust the BTUs. So in this parameter 14, we can go in and adjust the BTUs up and down. So even though it has the capacity or the capability of going to 95,000 BTUs, we only need 60. We're going to drop it down to 60 or 50, whatever the case may be. So in this case, we drop it down to 50,000 BTUs. Now what does that do? Well, if we didn't adjust it, when we have that 30-degree temperature outside, we're going to get 27,500 or 57,500, which is our target, as we mentioned earlier. But now we've gone into the controller, we've said, hey, we don't need 95, we only need 50,000 for this house. So the controller automatically knows that the target temperature, right, the maximum BTUs at our design outdoor temperature is only 50,000 BTUs, a lot lower than 95. So what does it do? It flattens the curve. So now at that same 27 or 30 degrees outside, I'm only delivering 27,500. That's the advantage of Outdoor Reset. So it really allows you to customize each and every application. You can customize it based on your outdoor design, but then you can also customize it based on your actual heat load. So you're never oversizing the system, because we can dial it down and we can target it. And given that we've got full variable speed pumping, we've got full variable speed ECM, there's nothing about being oversized or undersized. And in fact, there might be an advantage to using the larger coil, because, as you say, we can operate at a lower water temperature and deliver the same BTUs. Better for our gas appliances if we're trying to get full condensing. In addition, what was I going to mention? In addition, our 18,000 series cabinet size is going to be a little bit bigger than our 14,000, but we can attach a B-sized cabinet or a B-sized case coil on top, or a case coil that would fit a B-sized cabinet we can put on top without any transitions. And on the return, we can use a 16 by 25 filter rack. So again, there are some advantages of using it. Price is a little bit more because it's a bigger cabinet, little bit bigger blower. but there's some trade-offs as well. So all to say, we're talking about outdoor sensor and what the advantage of that is, and this is it. We can dial in our design temperature depending on where we are in the country, and we can dial in the heat load as well. So two important parameters. Now again, you have to have the ability in your software to adjust these parameters. We at iFLOW do, so we're able to adjust these, and again, dynamically adjust the performance of the system to exactly match what you have in the home. Fully customized, home by home by home. Now, another thing that iFLOW does, we have iFLOW, where we have Wi-Fi. So we have Wi-Fi on all of our units except for our base model. So this Wi-Fi module will come with each model, and it plugs into the board, and you can then attach it somewhere on the side of the unit or on the ducting. Don't put it inside the case because the case is metal and it's going to severely restrict your signal delivery. But other than that, just mount it on. There's this two-sided tape on that for your convenience. So we get the Wi-Fi module. Now, what can you do with the Wi-Fi module? Well, we have an app that is designed for Apple's iOS, and it's designed for Android. So you can use both on whichever phone platform you're using. What you can do with the Wi-Fi is you can connect your air handler now through your home network, through the app, and remotely monitor the app. You can get error codes. You can adjust, if you're in smart mode, you can adjust the temperatures on your system. You can set your setback. You can even go without a thermostat. Right? In smart mode, we can use our return air sensor and our supply air sensor as thermostat proxies and deliver and adjust your system automatically through smart mode without ever needing a thermostat. To do that, however, we do need to run the blower even at a very low speed, but just to circulate so we can actually detect the temperature, and when it starts to drop, then we'll top up the heating and the cooling as needed automatically. So lots of advantages to the Wi-Fi system. The other is support, right? Just as you could get support for your laptop from HP or from Microsoft, if it's an office issue versus a hardware issue with HP. But again, we can supply some on-site support with your permission, right? If you want us to assist, give us permission. We'll come in and we can assist you with the setup and an operation of your unit. So this is what the app looks like. This is the Homeowners App. You've got the ability to set your heating, cooling, circulation. You can set setback on that. You can have different schedules, Monday through Friday, then Saturday and Sunday. So 5 and 2, or 5, 1 and 1, or all 7 days the same. You can do zoning. So when we go into zoning, iFLOW can do zoning. We can do up to 4 zones per our largest model. Well, I can set, remember, my basement, main floor, second floor, third floor, and I can set the different parameters for each of those zones. So lots of flexibility there. On the contractor side, there's a Contractor App and there's a Homeowner App. On the contractor side, it's going to give you some technical feedback, right? Some technical output. You're going to get from the different zones, you're going to get the supply air temperature, the return air temperature, the supply water temperature, the return water temperature, the blower speed, the humidity level, the pump speed, the BTUs that you're using, the outdoor temperature, lots of information that you can then quickly use to assess and determine what might be wrong with the unit before you even go over. So you've got a good chance of taking what you need to site and being able to troubleshoot and rectify the situation easily. You can actually, from the Contractor App, you can go into test mode and you can run the blower, right? Test the blower, test the circulator, test any of the relays that we have to see if the equipment's coming on or off. So even without being on site, you can troubleshoot the unit, see what the resulting effects of, right, blower motor on or circulator on, and see, and then again determine what you need. The other advantage of having the for the contractor is if you have multiple units set up, they can all be on your phone. So if you have 10 different iFLOW locations where you've installed the iFLOW, you can monitor each one of them and without problem at all, right? You go in and you get a full listing of everything that's there. So for property managers, that could be helpful. For you as contractors, that could be helpful. You've got everything on your phone. You can remotely monitor the performance of all the systems. You get some warning alerts on your phone if any of the systems go down, so you may know it before the homeowner even knows it. We've got some auto backup and auto rectify settings that will automatically try to keep the system running. Right? If one sensor goes down, right? If our supply air sensor goes down, well, maybe we can use the evaporator temperature sensor as a proxy for that, or maybe we can use the delta T and look at the return water temperature and estimate, well, if the return water temperature is here, the return or the supply air temperature is quite closely correlated with that, so we can estimate some of those parameters. So again, we've got that auto rectify functionality built into our software. And then we've got broken thermostat mode. So if we can set some boundaries. So let's say, hey, if I get if I have a call for cooling and my return air temperature is 55, do I really need cooling? No, I can assume that my thermostat's not seeing the right temperature and it's just continuing to call for cooling. So I can set those thresholds and actually turn the system off. And that's kind of the range. On the heating side, same thing, right? If I'm heating and I'm sensing the return air temperature is now, well, 78, 80 degrees. Hey, why am I going up so hot? I shouldn't need it that hot. Could be the thermostat's broken. Could be the thermostat's not seeing the temperature for whatever reason. Again, we can set that upper limit and say, okay, if you ever get to a situation where the return air temperature is 82 degrees on a heating call and you have a heating call, just turn it off. We'll identify that as a broken thermostat. So you can set those limits on the iFLOW. We think that going in and setting up, so you can go into pairing mode when you go and set up the unit for the first time, even if there's no internet, right? Maybe it's new construction, homeowner hasn't moved in yet, house isn't even sold yet, but you as the contractor in that RNC project is setting up the unit. You can pair to the unit just as you would pair to your Bluetooth stereo, and you can go into your app and you can actually set it up. You can set it up for the design specs of that house. Set it up perfectly, have it run, and then when Mr. and Mrs. Jones do move in, 3 months later, 6 months later, whenever the house is sold, they can then connect the unit to their home network, and then we will pick up and match the two units on the back end. We think that's a lot better, right? This is one of the more advanced modulating condensing furnaces in the market. We think our setup is a lot easier than trying to go through dip switches and set it up that way. Zoning. So iFLOW incorporates zoning into its system. I showed you the 4-zone board and where all the thermostats wire in and all the zone dampers wire in. Why do we look at zoning? Well, stratification is a reality, right? Stratification has been around for forever. We know that heat rises. It's going to rise in the home. The basement's going to be cooler than the upper floor, no question. Wherever the thermostat is, right, typically on the main floor in the hallway, that's going to be the most comfortable because that's going to be at temperature, but the other two floors will likely be not as comfortable, maybe even uncomfortable. So in this example, for example, the upstairs is 82 degrees. Well, the basement's only 64 degrees. What if we equalize those two? Where would we end up? Somewhere around the middle. But hot air is naturally going to pool in the upper floors, managing that system in terms of where do I put my thermostat. Now, some manufacturers are running remote sensors and feeding back to the main controller, but the problem is, if it's a single zone system, what do? Right? You can have the sensors there all you like, but if the upstairs is hot, you're going to have to bring on the entire system, right? If you need cooling upstairs, you're going to bring on cooling and it's going to cool the basement it's going to cool the main floor to get the cooling into the top floor. So it's very difficult in a single zone system to properly mix the airs and to get a comfortable temperature upstairs, main floor and basement, so that you can use all of the square footage of your home. We've been dealing with this for 50 years and it's still an issue. Doesn't have to be though. At iFLOW, we can zone the system so that we can deliver heating, cooling into zone by zone, right? If it's the basement, if it's the main floor, if it's the upper floor, we can deliver comfortable temperatures all day long, whenever you need it, into each of those zones without problem. And it's not costly, it's not difficult. We can group the zones by function, or we can group them by floor, for example. If we're going to group them by function, well, maybe we'll have the kitchen, the dining room, and the great room. Maybe that'll be one zone. And then the bedrooms and the bathrooms will be another zone. And then the basement could be a third zone. And then the room over the garage could be a fourth zone, or the attic could be a fourth zone. So there are a number of ways we can divvy it up, or we can go floor by floor. We can have, right, zone 1, zone 2, zone 3, zone 4, like in this diagram. So all to say, we can divvy up the house and the zones as we need, based on functionality or on square footage or floor. Our objective is to make every zone comfortable and every zone the same temperature when you want to use it. So for example, if nobody's using the basement, I can close that zone off. I really don't care what temperature it is. If nobody's using the bedrooms upstairs during the day, for example, if everybody's out at school or work, nobody's home, why do I need to keep these bedrooms at temperature at 3 o'clock in the afternoon when the summer sun is beating in through the windows? I don't. I can bring that on. I can go to my controller, my app controller. I can bring, okay, 5 o'clock is when the kids get home from school after, right, sports after school. So they get home about 5:30. I can set my timer so that I bring that on and have that room at 5:30 when they get home. I can have it at temperature. But from 7:30 when they leave to 5:30 at night, I don't have to do anything in that zone. I can just keep it off. But if if the grandparents are home, for example, or if one of the parents isn't working and they're on the main floor and they want that floor comfortable, okay, well, we can make zone 2 comfortable while turning off zone 3, 4, and 1. Right? Whatever strategy you want to employ, we can do it with zoning. Now, with our zoning, what we're suggesting is we have a supply and return duct to each zone. Why? So that we can do exactly what we said. We can isolate zone by zone and deliver the heating and cooling we need to each specific zone. If we have a common return, then we can run supply ducts to zone 4, zone 3, zone 2, zone 1. We can supply the heating and cooling as needed. But when we have a common return, we're going to be drawing the return air from all the floors. It's going to average out and come in. So our return air temperature is going to be the average from the home, rather than just specifically looking at one zone in particular. But if we isolate and are able to do supply and return ducting for each zone, then we can only deliver heating and cooling into this zone, into that zone, into that zone. That's where you get perfect comfort. I can make any zone at any time of the day its own thermal, or have its own thermal comfort, which is controlled by your app remotely if you want. So, all to say that we can, that garage that's over the room that's over the garage that's always too cold, always too hot, never getting the right CFM, make it that a zone. We can make it as comfortable as you need, no problem. The basement, right? Where the basement, you've got your AC unit down there, maybe there's a little leaking in the ducting, so the cold air is dropping into the basement, so the kids want to go and watch a movie downstairs. Let's say you've got a rec room in the basement, but it's cold. So in the summer they're grabbing a blanket to watch a movie where it's probably 78 degrees upstairs Does that make any sense to bring on heating for the basement, cooling for the upper floor? Why don't we just mix it around? Okay, we could. And if we're zoning each, I could easily say, okay, bring the temperature from zone 3, bring it down to zone 1, and dump the heat here, and take this cold air and dump it up here. Just mix it around, just these two zones, and interchange them. Right? I can just mix those two zones. They'll mix in the on the return air side, and they'll equalize, and then send out to both those zones. And then once they're equalized, we can say, okay, now do we need to bring on heating or cooling? So we're trying to, again, maximize the efficiency of the system. So again, we already looked at this graphic. We looked at the board, and again, this is how we do our zoning, right? This is a 4-zone system, so thermostat 1, 2, 3, and 4, 1 from each zone, and then we have our dampers. We have our supply dampers, our return dampers, and we actually have temperature sensors in each of our dampers, so we know exactly what we're supplying and returning from each of the zones. And then again, because this is a 4-zone system, we've got 4 sets of those. And then we output on the rest of it. So all of the zone control is built onto our controller. Why? To make it simple and easy. You don't have to worry about buying extra components, extra controllers. Everything is here with the unit. Everything's set for you. It's easy to connect through, and then we take it from there. In terms of accessories, we have zone dampers. We have an 8x8, 8x10, 8x12, 8x14, 8x16, 20, and 24. So the 8-inch, right? The 8-inch is where the motor is. That's on the side. And these are slide-in type. Right? So those are the dampers. They are 3-wire, right? So we have power open, power closed, and we have common. So you cannot use spring-loaded dampers with the iFLOW system. Spring-loaded dampers, you need constant power to keep that spring open. And because we're talking about longer run times, because lower inputs, less cycling, longer run times, if I need 60,000 BTUs, I'm going to run or if I need 15,000 BTUs and my heat source can run, I'm going to run for the whole hour at 15,000 BTUs. That's the advantage of it. So if I was using spring-loaded dampers, I'd be fully open the whole time. Power supplied continuously. I'd be using more energy than needed. I could overheat those motors. I could prematurely reduce the life of them because I'm using them, because they're open so much. Whereas when we're just power open, power closed, we power open for 7 seconds and then it's open, done, set. And then we power closed when we're finished that zone. Again, 7 seconds, that's all the power we're supplying. We do have round. We have round in 6-inch, 7-inch, 8-inch, 10, and 12. And that's the diameter, right? So round diameters we can fit into any. Again, here's our temperature sensor in each of the zones. And again, it's also 3-wire. So in terms of static, we can operate with that Gentech Eon ECM blower. Again, constant CFM. We can operate at low, medium, or high external static pressure. How do we do that? Well, so low is considered, let's say, 0.6 and below. Medium is from 0.6 up to 1 inch. And then high static would be anything above 1 inch. Why would we want to run at higher statics? Well, perhaps we have some smaller ducting that we want to use to run through the wall studs, through the wall, through the stud cavity, so that we don't have bulkheads and we're minimizing boxing. And so there may be reasons why we wanted it. It could be that our duct size, there's some restriction on our duct size that we didn't account for. What's going to happen to the blower? No problem. The blower is going to be able to automatically compensate for that little bit of additional restriction without problem and maintain the CFM. So again, you don't need to select a different model. All of our models are fully variable speed. You don't need to change any dip switch settings or anything like that. No. Why? Because we're using the outdoor sensor. We know what the temperature delivery in the home should be. We know what the BTU target should be. We know what CFM we need to deliver that. We'll maintain the CFM with the unit automatically. automatically. So there's a little bit of a degradation in CFM as we go up, but we've tested all of the units are available or high static capable. At 0.6 you're going to get 1425 out of the 18,000 CFM. Out of the smallest unit, 940. And then as we increase the static, there's going to be a little bit of a drop. So about a 20 to 30% drop depending on model, but just accommodate that. So if you're designing around a higher static, make sure you know that the limitation on the blowers are there. And this is all in the manual and it's all in the literature. We have blower curves that kind of replicate what we're seeing. So it kind of gives you an idea at the various statics and depending on the 3 different blower motors, right? The 14,000, 16,000, 18,000 series, what type of CFM you're going to be able to get out at the various static pressures. So for example, if we're designing around an 800 CFM, we can go to 800 CFM and say, hey, well, we can go right up to 1.25 inch static and still deliver on our smallest model, still deliver 800 CFM. Right? So that's how we could do that. And then if we're designing around a static, 0.8 inch static, then we can go to that and we look at, okay, out of our 14,000 we're going to get approximately 950 CFM. Out of our 920, out of our 16 we're going to get about 1200, and out of our 18,000 series we're going to get about 1380. So we know exactly whether it's designed around a static or whether around a CFM, what we're looking at. Now, when we're going to initiate the system, we can have our gauges in, have our manometer, and then we just increase the blower speed in 1% increments until we hit our static, and then we know, okay, this is the CFM we should be getting at the registers. And so there's one more feature that iFLOW incorporates into its PCB, and that is communication with the Navion. So this is unique communication only between iFLOW and Navion. We're not aware of any other manufacturer that's able to do that, and it brings really 4 distinct advantages. Number 1, the iFLOW and the Navion can communicate and coordinate on varying supply water temperatures. As we looked earlier, the GPM and the delta T are critical variables to delivering the BTUs from the water side into the heating side. So that flow rate, the Navion is actually going to communicate back with the iFLOW and tell us what the flow rate through the Navion is, right? So with the flow sensor in the Navion, it's going to relay back and tell us what the exact GPM rate is. And then the iFLOW can modulate the GPM rate based on the power supplied. In addition, we coordinate on supply water temperature. So we can tell the Navion, so based on the outdoor sensor for the iFLOW, and again, remember that outdoor sensor is determining the outdoor temperature so that we can target the right BTUs to deliver into the home. Right? Again, we can fully customize the rise and the run of that slope. So we're going to use that outdoor temperature to determine the BTUs we need. We know what the GPM rate is, so then we know what the delta T is. So if we know what the delta T is, we can tell the Navion, hey, I need this temperature because I need this kind of delta T across there. So they can increase or decrease the temperature as we need, depending on the season and the outdoor temperature. So that's iFLOW Navion communicating. Number 2 is critically important for maintaining efficiency. So as we saw, let's say we're using the NPE 240A2, which has a minimum input of, or a maximum input of 199,900, and has a minimum input, 15 to 1 turn down, so has a minimum input of 13,300. Let's say my heating load, let's say it's a warm, it's been a warm day, mid-October, but the evening is getting a little cool, so I just need a little bit of heating. So maybe it's 7,000 BTUs, 8,000 BTUs. But my minimum is 13,300 on that Navion NP248.2. So the Navion is going to cycle. How much is it going to cycle? Well, if I If I'm delivering 13 and I need 7, it's about half. So I'll be on for half the time, off for half the time. So it's probably going to run for 10, off for 10, run for 10, off for 10, and do that 3 times. But even when it shuts down, right, when the Navien shuts down and cycling, and it'll post-purge some of that heat out, we recover that. So we take that waste heat, which would have been waste heat, and we recover it back into the system. How do we do that? Well, the iFLOW and the Navien will coordinate, and the iFLOW will say, hey, I only need 7,000 BTUs, so I know you're going to cycle. When you cycle down, I'm going to keep my pump running. So the flow sensor still runs, so the Navien should think it's going to keep firing the burner off and on. But the iFLOW says, hey, you can cycle down, let me keep my pump running and scrub all of that heat out of the Navien heat exchanger, bring it into the hydronic coil inside the iFLOW, and then we'll continue to run the blower and deliver that into the house. So even when we're cycling, even when the Navien iFLOW system is cycling on and off because of very, very low heating loads, we're still recovering much of that heat because we're not post-purging it out. And that's very different from what the furnaces can do. You know, the furnaces, when they shut down, there's no recovery of that. All of the heat that they built up in the heat exchanger really goes to post-purge. And then when they come on again, they have to reheat their heat exchanger before they deliver warm air into the house. Whereas we are recovering that. So even though we can modulate lower than the furnaces, and we can even do better. So even though we're modulating lower and getting better efficiency, even when we're cycling, even when we shut down on very low inputs, we're still not losing all of that heat. We're recovering as much as we can into the system and delivering it into the air. Number 3 is we enable that outdoor reset. So we talked about the outdoor reset and the varying temperatures, but we enable that on the Navien tankless without the need for the H2 air kit. So the Navien has created an H2 air kit that interfaces with air handlers. It basically doesn't do much in terms of interfacing. It just sends the signal. It sends an RNW signal to the air handler to bring on heating. But it also has an outdoor sensor connected to it. So it will bring that temperature variability capability to a Navien tankless when you're using the H2 air kit. But the downside of that is the H2 air kit is designed to work with the A models or A2 models. And when you hook the H2 air kit up, you lose the domestic recirc functionality of the pump, because the pump, when it's hooked up with the H2 air kit, becomes solely dedicated to heating. Right? So it won't run to recharge the buffer tank. It won't run domestic recirculation. It won't allow you to run domestic recirculation through a crossover valve under the faucet. So the domestic recirculation, internal and external on the A2 models, will be disabled if you're using the H2 air kit, because the pump is being used for space heating exclusively. With the iFLOW, we can use the communication and enable, because we don't need the H2 air kit, you can still use that pump inside the A2 model for domestic hot water circulation. Now that said, the design of the A2 is different from the A model. With the A model, you had a recirculation return port. You connected your recirculation return connection to that port, and the pump drew the water from there and went into through the flow sensor and then through the unit, heated up. There was no problem. You could run your air handler without problem and still run dedicated recirc. With the A2 model, they're doing things a little bit differently. So let's take a look. The last point, it eliminates the need for a domestic hot water priority switch. We do that by coordinating between the iFLOW and the Navien and looking at the flow rates and the temperature differentials and deciding what's a true domestic call versus what's a circulation call on the heating side. But anyway, let's go back to this number 3, and we're going to look at that for a couple of minutes, only because this again will be a unique feature that only iFLOW and Navien are able to do in the field. But enables you to run your air handler but maintain the domestic hot water circulation capability. So let's look at the NPA2 domestic water recirculation with the iFLOW. So here's the Navi recirc. Okay, So the Navi Recirc, and this is designed for recirculation, where you have a dedicated return line, where the dedicated line is available. So what you do out of the hot line of the Navien, you tee off to all your fixtures. From the furthest fixture, you're going to tee off, and you're going to bring that return water back for reheating. It's going to reheat up, and it's going to go out the line, so that whenever any of these fixtures pull off, there's a very short run off the main hot line, so you're going to get hot water very quickly. You want to make sure you insulate the line completely so that you're maintaining all of the heat, or as much heat as possible, inside. But again, that's what it's for, and you can come back into the domestic hot water return fitting on the A2 model. In this, you would set your manual diverting valve to external, so that you're pushing all the water out, and then it's coming back through here. The pump will pick it up and then draw it through and push it through the heat exchanger. So that is where a dedicated line is available. But one of the advantages of the A2 model is that they wanted to allow for recirculation where a dedicated return line has not been installed. So in most retrofits, for example, there was no recirculation line initially plumbed in. Or if it's a new construction, you save the fact that you save running a line from the furthest fixture back to the unit if you can use a crossover valve. So what happens now? Well, again, from the furthest fixture, so same as here where we installed this T at the furthest fixture, we're going to install the Navien Recirc fitting at the end of the line, at the furthest fixture. So what happens now? Well, the hot comes out, feeds all the units on the line, feeds this fixture, but then when nobody's drawing hot water, that line is going to cool down. Right? If we have a dedicated line, we will automatically recirculate this when the buffer tank drops in temperature. And we're using the buffer tank as a proxy for the start and stop of the line. So when the buffer tank needs reheating, it's going to reheat this entire line. Now with this, we've fed out hot water, but let's say over time, let's say it's an hour and we haven't run any hot water, the line is going to go cold. Right? So the entire line will drop down to ambient temperature, 70 degrees, 65 degrees, 68 degrees, somewhere in there. But we've got this fitting installed at the end of the line. So when this fitting, right, when this the Recirc valve, the Navi Recirc valve, sees a cold temperature on the hot line, it's going to open. And when it opens, and when the buffer tank also drops in temperature, the pump will come on. Now, because this valve is open, we're able to run out the hot line down the line through this Recirc valve into the cold line. So that's the difference. This has a dedicated return line, so we're not using the cold line. We're using the hot line. We're taking a T off, we're bringing this back to the recirculation. So not using the cold at all. See, it's not connected on the cold side at all. With the Navi Circ valve, what's happening now is that valve is allowing the crossover from the hot to the cold. So we're using the cold line as the conduit back to the unit. And we're pulling in and then going through heating up out to temperature. And then that whole line, once this line heats up, then the valve will close and that circuit will no longer be available. And it just does that repeatedly. So whenever it sees the line cooling, the valve will open. When the pump comes on automatically based on the temperature of the buffer tank, it's going to push through this whole circuit and warm the whole line up. So that is the Recirc. That's the Navi Circ. But so this is what's happened, kind of explained it there. So the water goes across the valve and then back around. When we hook a hydronic air handler to an Navien A model or an A2 model, again, using the H2 Air Kit as I explained, the pump inside is dedicated just for space heating, right? So we're using the return line, which was the domestic recirc line, we're now using that for the return line from the air handler. So it's no longer able to do the domestic recirc, which means you no longer have domestic recirculation. So with the buffer tank on the outlet, as I mentioned, in winter, because we're running heating, the buffer tank will stay warm. But in summer, you're going to have that half a gallon of water on the outlet of the heat exchanger. It's going to cool down to ambient temperature. So when you open a faucet, you're going to have to actually wait and evacuate that extra half a gallon of water before you get new hot water. So on a shower, that's another 15 seconds of water before hot water gets to the fixture. May not be that big a deal, but in some cases where water is a premium, that's important. So let's look at the A2 model now with the reconfiguration and see what happens. So we have a crossover valve here, and the crossover valve is open. The Navien sees the buffer tank. So let's just preface that by saying, okay, so maybe you decide to install an external pump, right? So you're like, okay, well, I still want to use the pump inside, so I won't use the H2 air kit, and I'll use this pump for domestic recirculation, and I'll include another pump for the air handler. Okay, you may think that would work. So let's say you decide to do that. You install an external pump for space heating, so it's connected to the air handler, and you run your domestic recirc as you expect. Now, you have a crossover valve here, so when that crossover valve opens, and when the temperature in the buffer tank drops, the pump is going to come on, it's going to push through this circuit, and it's going to hit this T, and it's going to do what? It could go this way, and through this valve, and back around. So it could do that, but it can also go this way, through the air handler, and back around. Even if this pump isn't on, this pump is pushing out through. So how is it going to determine which way to go? Wherever the pressure drop is least, right? If it's going to take the path of least resistance. So if I've got, if this valve is creating a big pressure drop and this is no pressure drop, it's going to go this way. If this is lower pressure drop than the air handler, then luckily everything will go this way. Or it could be a mix of both, right? Majority of the flow could go one way, but there will be some going the other. So all to say, when you're hooking up an A2 model with an H2 air kit, you're going to lose the domestic recirc functionality. The crossover or the dedicated, both you're going to miss. And you're going to miss the internal buffer tank recharge. So whether internal or external, no recirculation, no domestic hot water recirculation. And then if you try and use an external pump and don't use the H2 air kit, then you don't have the outdoor reset. Right? You don't have the temperature variability, so you're going to have to set the Navien at the temperature you're going to need in the middle of winter, and you still don't get the recirculation you want because you have this crossover, and that's creating a loop in your system. So, iFLOW Navien communication. So what we're doing now, without the H2 air kit, again, because we can communicate with the iFLOW and the Navien, we don't need the H2 air kit. We still have outdoor reset, right? We're using the outdoor sensor connected to the iFLOW, and we're relaying the temperatures that we need to the Navien. So we're calling on 140, 150, 160, right? So without the H2 air kit, we're still able to get the outdoor reset. We still get the shutdown functionality, right? The post. The flush, right? The heat flush out of the heat exchanger on a post purge shutdown. But then we also have a two-way valve. Right? This two-way valve will install on the iFLOW, and it's going to be normally closed. It's only going to open when there's a call for heat or when we're running an anti-stagnation circuit. So in the summer, if it's July or August, we want to make sure we're moving this water through this loop so that the next time the faucet is open, we get fresh water coming into the entire circuit. So it's only going to open during those two cycles, right? heating on or anti-stagnation. The rest of the time it's going to be closed. So if this valve is closed, now where's the water going to go when the Navi recirc valve opens and the temperature at the bottom of the buffer tank tells the recirc pump to come on? Now this pump's going to come on, push through, and try and go this way, but oh, valve's closed. I can't push anything that way. I have to go this way. Has to go this way through the valve, back around into the unit, and you have domestic hot water recirculation. So, without the H2 Air Kit, Navien, iFLOW communication, you get all the goodies that you'd have with the H2 Air Kit, including the additional bonus of having the shut down the hot water or the flush after post-purge. And you also get the functionality of the domestic hot water recirc, whether it's internal only or whether it's external dedicated or external with the crossover. All of those options will then be available with the iFLOW and the Navien. So again, this is going to be available in the late fall of 2021. So, which units can we communicate with at this point? The A2, S2, the H model, the NCB H model, all have communication, all are models, except for our base models. So be careful. The 140,000 are also called 14,000B, 160,000 or 16,000B, 180,000 or 18,000B. The chipset on these B models is not large enough to cover the communication with the Navien. So you don't have that, and you cannot upgrade for that. The wiring is different between these two boards. So unfortunately, if you have a B model, you can't use communication. So if a B model, you can definitely use the Navien H2 Air Kit with this and get the outdoor reset without the communication. But if you have the W's or the D's or the Q's, then you can definitely use the communication cable between the Navien A2, S2, 8, NCBH, obviously the NPA and S from the old ones, and then soon to come I think most of the boilers will have that functionality as well. But right now those models have it. Okay, so how do you connect the two? Well, it's simple. There is a communication cable. Now it looks very much like the Navien multi-link cable, but it is not. The pins are different and the wire shielding is different, and it's going to be labeled differently. You're going to have an iFLOW end and a Navien end. So it comes in two lengths, 16.5 feet and then 33 feet, so 5 meters and 10 meters, right? So two lengths, and it connects at the same place the multi-link cable would. So you can't use multi-link and iFLOW Navien communication because we're using the same port. So it's either one or the other. So this will be more for single unit with an iFLOW. If you're using multiple Navien units on the wall for domestic hot water, for example, then you'll have the multi-link, and then you wouldn't use the iFLOW Navien communication. But it connects to the side of the display on the Navien, and then it connects to the board on the iFLOW. Now, I will mention that the cables that we use for pairing are optional. Optional because we don't know, if you're using a Navien or if you're using another heat source or a boiler or whatever the case may be. So please order it as you need, but that communication is available. So how do we do that? Well, then we go on to the Navien. We go into the installer menu, go into the application setting, select air handler communication. We enable the air handler communication, and then the two will start talking. As soon as the two start talking, there will be a decimal point on the second dot, decimal point on the second digit on the Navien or the iFLOW display, and that will tell us that we've effectively connected with the Navien unit. Right. To connect both of them, I would shut the power down to both of them, connect the cable, and then power them both back on so they can both see that communication right from the start. Okay, so one other component, optional component that we have put together is the Easy Plumbing Kit. We do that to make all of the installs as consistent as possible, but also to make it as easy as possible. We know there will be a lot of HVAC contractors that aren't as comfortable with the plumbing side, so if we use the plumbing kit, we minimize that. And this is what it comes with. So it comes with the isolation valve kit, comes with the pressure relief valve, comes with the mixing valve, comes with an air vent, comes with a pump and the connection, and then the connection over to the cold side of the mixing valve. So most iFLOW installations will require these same basic components. The system is all NSF 32 low lead certified. It's a standard plumbing kit, again, to make it speedy and less costly. So again, hot side, you get the isolation valve kit, right? Hot and cold, you get the mixing valve, you get the pump with the unions and the check valve, you get the air vent, and you get the supply and return connections to the air handler themselves, and then you get this crossover valve. So that's what comes with the system. Here's how it would look installed. So I have my tankless, again, mixing valve, pressure relief valve with the isolation valve kit. You have your drain ports if you want to flush the heat exchanger. You have your connections to the iFLOW, and then the return connection back from the iFLOW. You have this crossover. You have the air vent, potable rated air vent, connections to the top, mini expansion tank, the Grundfos 1558 with the unions and the check. So that's everything that comes with the system. You know, if you're spread apart, like if they're not that close, then all you have to do is extend the piping between. All the rest of the components remain the same. So to get a visual of the system, this is what it is. We have the isolation valve kit, pressure relief valve, mixing valve. We've actually switched to a Calefi mixing valve on this. We have the crossover, cold, coming over from the cold side into the cold side of the mixing valve. So we have hot, cold, and then mixed temperature going out. We have the cold side, which again, you have the drain, right? The drain valves. You have the return from the iFLOW, air vent, pump, and expansion tank. So everything there is what you get in the kit. If you don't need that kit and you're just running with a boiler, for example, and you want the pump, well, we can supply just the pump with the check and the union fittings without problem. And what we'll finish on is just troubleshooting. So again, on this whole concept of making things easy, quick, simplified, easy for the contractors, easy for the industry to understand. Again, we're going back to our board, and I wanted to show you all of the LED lights. So we've forced these on, but all of these LED lights refer to what we're seeing from the thermostat. So in this case, I know that I've got all my thermostats are calling at the same time. I've got red for heating, yellow for circulation, and G for cooling. And we've got the same. Now we've forced these on, that's why you're seeing it like that. Normally you wouldn't be calling for heating and cooling at the same time, of course, from the same zone. But that's how it would look. When those lights come on, then we can see a corresponding output. So these are our inputs, these are our zone dampers, and these are our outputs. So when I get a call from a contractor and I ask him to send me a picture of the board as it's operating, I can see exactly what's calling. So I know, okay, my thermostat is seeing a call for heating on zone 3. Not a problem. That means the zone dampers for zone 3 should be opening. So I should see some power here when these are opening and closing. And if I've got AC on, if I'm running with a heat pump, then I can see, okay, I've got my relay for my compressor is on, and I've got my relay for my reversing valve is on. So I'm delivering heating from the heat pump into zone 3, for example. So we can easily diagnose what's coming in, we can easily diagnose what's going out, and if there are any problems, we can then more easily, more quickly troubleshoot the system. And you know, we've been very lucky in that there are very few issues in the field, and the majority of them we can solve over the phone. I would say 99.9% of the calls we get are solved over the phone without any modification, just because we're able to fully diagnose without getting the multimeters out and trying to figure out what's going on. We can just follow the LED lights around the circuit and diagnose it that way. So we'll end it there. Again, my contact information. If you have any questions about what was discussed, if you want a copy of any of the information, please feel free to email me or call me on my cell or on toll free, whichever you like. Visit our website. We'll put these videos up on the website for your convenience. But again, thank you for your time. If you have any topics that you would like discussed, send them on and I'll be happy to do a video up on them. But again, thank you for your time. Thank you for your interest in iFLOW, and we hope that we've answered some questions with our Part A and Part B, and that you'll consider using an iFLOW Combi system for your next HVAC project. So again, thank you.